We are going to wait a few minutes before we start to give an opportunity to latecomers to join. I'm Stefan Orovich. I'm standing in for my colleague Anne-Catherine Debian, who had a last-minute issue and is not able to moderate this webinar. I'm a senior advisor at the user support service of WEkEO, and I'll be introducing the speakers and giving you some high-level information about WEkEO. In fact, we can even start by introducing the speakers. So today is a special webinar. We're not going to teach you, we're not going to train you or show you how to use the WEkEO DIAS in a particular technical setting for particular applications. We're going to show you that the DSs, the DSs in general, and this DS in particular, are in fact also tools to produce, let's say operationally, industrially, some applications, some products in some cases, some portals in other cases, some apps, some applications that can be used by citizens, businesses, etc. So we have quite a nice panel today with examples that are very different. Examples from, let's say, trying to bring science closer to citizens with our colleague from Varvis Tsonsos from NASA Joint Propulsion Laboratory. We have colleagues from Magellium who are going to tell us how they have used the WEkEO DS to produce a product of the Copernicus land monitoring service, which is the high-resolution snow and ice project. And then we'll have Ater and Bas from Lobelia presenting an app that they've developed to provide air quality monitoring and forecasts at very high resolution to citizens in selected cities in the EU. So that's this is our panel. I'll just give you a very brief introduction. And this anyway, I guess if you've registered, you've already seen the agenda. The house rules, very simple, and a lot of you, I guess, have already participated to prior editions of these WEkEO webinars, is please use the question and answer button to ask your questions. Go to the chat room, and then we will select the questions and put them in a special tool to be able to answer them. So that's how you ask questions, but I think this has been presented. This is our 12th webinar, and I think we've presented this 12 times. So I think it's pretty clear by now. And that's it. So I'll ask you, Anna, to move to the general presentation so I can quickly summarize the main features of the WEkEO DS. In any event, I won't go into details because A, we've been making that presentations already many times, and B, as some of you already know, all of these webinars are recorded and they're made available on our YouTube channel, so it's easy to have access to them. Can I have the other presentation, please? Hello? Ah, it's coming. Here we are. So today, again, we want to talk about opportunities of new developments, large-scale new developments. For those who join us for the first time, what is WEkEO? It's one of the services that provides access to the Copernicus Sentinel data and to the information and forecasts and models, etc., provided by the Copernicus services. It's a joint venture, basically, between EUMETSAT, the European Organization for the Operations of Meteorological Satellites, the European Center for Medium-Range Weather Forecasts, Mercator Océan International, and the European Environment Agency. Its main features is that it's like a one-stop shop, a single access point to all the Copernicus data. The second important point, it's fully cloud-based, which means you only need to download the final result of whatever you're doing. And you can find in the cloud not only the information, the data, the satellite imagery, etc., but also some virtual machines, GPUs, etc., that can be used to process the data that you are interested in. Last but not least, it is the DS that has the most developed user support service with high-level experts in about all the Copernicus areas or direct access to such experts. Why is that? That's because the partners that have come together to create the WEkEO DS, these partners are the producers of a lot of the data that is being distributed by Copernicus. You have around the table the producers of the Copernicus atmosphere monitoring data, of the marine environment monitoring data, of the land monitoring data, of the climate change service data, at least. And you have with EUMETSAT, the provider of the largest part of the Sentinel-3 imagery. So that is pretty unique. You have all the information from all these satellites is available in the catalog, together with the infrastructures, the tools, lots of tutorials, wikis, FAQs, etc., and a marketplace. That's a new feature in which you can see what others have developed by using WEkEO, which might trigger some ideas of businesses, services, or scientific applications that you might want to deliver through that interface. There's quite a lot of data. It's in the order of petabytes, 225 different data sets. So you're pretty well covered with that amount of data. The infrastructure is distributed in the sense that the data is not copied from its original source. It is basically fed from its original storage, which is guaranteeing that A, you have the latest, very latest data available, B, that there is no latency, and C, it's important these days, because we don't copy the data, we minimize the cloud storage requirements, and therefore we are the most eco-friendly and carbon neutral of all the DSs. Our users, well, they're all kinds of institutions, companies, scientific centers, R&D, academia. Basically, the service was configured to be usable without having being a postdoc in remote sensing. Of course, some of the translation from data to actionable information does require technical skills, but you can already discover quite a lot of Copernicus data and quite a lot of information by just browsing through the data viewer that is included in the WEkEO DS. The service has a free of charge layer in which you can, again, fetch, visualize, and download data. You just need to register, basically, to be able to download, etc. And if you want to start using virtual machines, processing power, graphic processing unit, etc., then you need to pay. There are different payment plans that go from the light, rather not too expensive one, to really fully professional and industrial prices. It's important to note that you, at the bottom of the screen, you'll see you've got trial periods that are rather generous, up to 5 months for the light one. And I think our commercial marketing department is also generous in sometimes granting extensions to these trial periods for, let's say, non-profit applications, universities, research centers, etc. We're happy to see that through WEkEO there is a global interest in Earth observation. In our previous 11 webinars, we've had registrants and participants from 44 countries. And I did see before we started that we had quite a number of visitors today and participants from all over the place. So good evening to some of you, good morning to others. But that's pretty nice to see such a strong level of interest in our webinars. Again, everything we have done since day one has been recorded and is available on our YouTube channel, which you can access to our portal, so no need to take too many notes. It's all registered, and you can replay any of those, knowing that some of the webinars were configured for beginners and others were configured for experts. That concludes my general presentation. I encourage you to follow our social media, where we try to present interesting applications and use cases of WEkEO, where we try also to showcase what other people are doing to a large extent. So that's it for my presentation. So we will now move on directly to the first speaker. The first speaker, Vardis Santos, will present CEO's Coverage, which is an initiative, cloud-based platform that was launched as to support interagency ocean data for open science. So the idea is really to make the information available to a wider public. Vardis, short bio, is a biological oceanographer. He works at NASA. Don't need to explain what NASA is, at the Jet Propulsion Laboratory, I guess in Pasadena, California, and where they don't only do jet propulsion, they also have a significant Earth observation activity. His main technical expertise in the previous years has been looking at the NASA Salinity satellite, and he now serves as the lead of this CEO's Coverage initiative, which he will now present from the Jet Propulsion Laboratory. So Vardis, it's an honor to have a speaker from NASA, and we're grateful. I think it might be very early, well, late at night or early in the morning for you. And I now, without further ado, pass you the virtual floor.
Yes, thank you very much for that kind introduction. Can everyone hear me and see my screen okay?
Yes, sir.
Thank you very much. So yes, hi everyone. My name is Vardis Santos, and I'm based at the NASA JPL. And today I'm going to give a brief overview of the coverage initiative and the technical project that I oversee, and emphasize really how we are using the WEkEO cloud infrastructure to support this project. Okay, so there's a great connection with WEkEO and CMEMS for quite some years now, actually, for the last couple of years, roughly. We're utilizing a range of CMEMS data sets in this application, and we're also leveraging the WEkEO Copernicus DS platform, in addition to NASA Amazon Web Service cloud infrastructures. And part of this project is really about how we can integrate across these emerging and new cloud infrastructures to provide more seamless access across agency repositories. So this project actually is a collaboration within CEOS, the Committee on Earth Observation Satellites, which is a coordinating body between the various space agencies involved in Earth observations. And there is both US and European Space Agency participation. So this slide basically summarizes what this activity is about. It's a formal initiative within CEOS. It's a cross-cutting collaborative effort that involves the 4 CEOS ocean virtual constellations. So for sea surface temperature, ocean winds, ocean color radiometry, and also altimetry, so ocean surface topography. And there's also a strong connection with a couple of GEO initiatives, Marine Biodiversity Observation Network, and also...
Sorry for this. I'm not sure if your slides are turning. Can you just test? I don't know if everyone can see the slides.
Can you see my second slide?
No, we're seeing the PowerPoint interface. We're not seeing the slides moving, in fact.
So can you maybe go into full screen? Just, sorry, tech support.
Yeah, I am in full screen.
Then you should share the other screen. You might have 2 screens.
Have 1 screen.
Okay.
Oh, that's...
Can you just go out then, and I'm going to share here.
Okay, so I'll stop sharing.
So...
I'm sorry about that.
No worries. So we're going to do this here. There you go. Voila.
Okay.
Can you please try here at the bottom bar? The bottom.
Where you see 1 out of 11. Yes.
See? I just did it for you.
It's being blocked by my taskbar.
Can you see it?
Maybe I can ask you to advance the slides.
Please go ahead. I'll do it for you. Please go
ahead.
Yes,
so I'm on this one.
Please go ahead.
Yes. So this is where I am. So basically, the motivation of this project and what we're trying to achieve is enable more widespread integrated use of interagency satellite data in support of ocean science and applications for societal benefit, and to address some key constraints to access and synergistic use of these multi-sensor Earth observations, particularly for newer and emerging user communities that have a need for this information. And we know that this is a response to a known need for the ocean community for more integrated access to data and analysis-ready form in support of some of these UN sustainability goals relating to marine biodiversity and ecosystem-based resource management. So the primary goals is to implement this technology platform, providing access to these complementary satellite and in situ datasets from distributed sources, and provide some value-added data services on top of those. Provide access to a coherent set of global interagency data products from these 4 ocean virtual constellations at a common baseline resolution, with a focus on higher resolution data sets next. And we don't just want to implement a technical system, but we want to demonstrate the utility of the technology to support a pilot ecosystem application related to high seas fisheries. Coverage has adopted a phased development approach. Last December, we completed phase B, which was implementation of this prototype capability. And in June, we kicked off a phase C activity that's an 18-month project that I'll describe a bit later. Our whole approach is to try to be as community-driven and stakeholder-focused as possible, adopt open source data principles, and also the fair data principles relating to interoperability and the like. And we have an advisory board comprised of our stakeholder organizations that provide some guidance and overall governance of the project. Next slide, please. Can you advance? Yes, thank you. So this slide is a schematic that summarizes the distributed architecture that we implemented during our Phase B prototype for the particular ecosystem application that we focused on. The red dots are our 2 satellite data nodes on AWS for the JPL, NASA JPL node, and on WEkEO at EUMETSAT for the European Copernicus marine datasets. And both these cloud nodes support our full software stack and provide access to the respective European and US satellite datasets. In addition, we are connecting dynamically to some in situ data providers in Australia, the Integrated Marine Observing System and CSIRO, and also the NOAA, IUS Animal Telemetry Network. We also have some other data providers that provide these some of these fisheries data sets. And we are actually hosting those data sets because they don't serve those out in an interoperable form. So the list of data sets that we are focusing on are kind of listed below. Some of the in situ data sets include these spatial catch and effort species data sets, animal telemetry, so electronic tagging data sets, and products from AIS on fishing vessel movements that are provided by Global Fishing Watch. Next slide, please. So the next couple of slides illustrate some of our prototype data services. You can see the kind of deployment that we have going in these cloud environments, both on AWS and on WEkEO. They involve deployment of a Kubernetes cluster, Docker containers with our software that includes this science data analytics platform, and also our on-Earth image tiling service, amongst others. Interfaces to the data are through Jupyter Notebooks and also APIs. The picture on the left illustrates some the Jupyter Notebook with some code that allows you to perform different kind of summaries of large-scale satellite data sets through this SDAP platform. And the whole concept of this is to enable data science without having to download the data. So you have on-site virtual computation capability, and essentially you just can download or see the results. Next slide, please. Okay, we also have an integrated visualization capability that allows us to overlay and visualize different kinds of satellite and in situ data sets. Some of these panels provide some examples. So this is another open source software development, the Common Mapping Client that's been developed at JPL. And it provides integrated visualization capability for both satellite and in situ data. One of the unique features is that it allows synchronized horizontal and vertical views of the data and their evolution over time. So, which is important when you want to explore coherence between these different data sets. And there's integrated data search capability as well. The tool also allows you to do a one-stop data subsetting operations on both the satellite and in situ data sets. Next slide, please. Okay, there is also in these prototype capabilities, there's an integrated search capability that allows you to inspect what data sets are currently in the system. And this integrates metadata from different agency repositories, including NASA's Common Metadata Repository, FEDEO, which has the metadata for the Copernicus system, also from IMOS in Australia and CSIRO. And you can do the typical kind of keyword-based search, or you could use the faceted filtering to narrow down the selections of data sets that you may be interested in. And what you get back is a description of the data and the access point to get at the actual data in our system and or actually from the source repositories as well. Next slide, please. Okay, and we've implemented a website through which you can access these prototype data services. There's a basic description of the project as well. There's a resource area where we provide some technical documentation, tutorials, and some videos. There's a news area where basically we post on events and announcements. And we also have a coverage YouTube channel and a Twitter feed where you can find more materials on the project and also where we release announcement. We have integrated Google Analytics into the site, so we have detailed metrics on who is accessing the site and what features they're most interested in. And there's been quite a lot of interest. We've had users come in from more than 77 countries last time I looked. Next slide, please. As I said, the community outreach and stakeholder engagement is a key aspect of this project. We've hosted 3 workshop events in the past year, including a meeting with folks at EUMETSAT, a workshop event with EUMETSAT and at Ocean Sciences and at ESIP. And in fact, we're planning on a further workshop event in February at the next Ocean Sciences meeting in Hawaii. And of course, we've presented at multiple conferences and in different forums involving some of our stakeholders for CEOS and others. Next slide, please. So we've, as I said, in June, we kicked off this 18-month Phase C activity, and where we'll continue this stakeholder engagement. But in terms of on the technical side, the emphasis is on hardening and further expanding some of our prototype capabilities. emphasis on higher resolution data sets and forward data streams and near real-time data. We want to expand the thematic application use case from the current one to a couple that have a more regional focus on regional ecosystems for the Sargasso Sea and also for the Eastern Tropical Pacific. One of the things that we're also looking at, assuming we develop something that's useful to the community, is how we can potentially operationalize, coverage in future. So we'll be working on a sustainability plan. And part of that also involves engagement on the UN Decade of the Oceans. And we've submitted an ocean shot concept dealing with next generation data infrastructures for a digitally integration ocean observing system. So we look forward to working with other groups and developing this further. And I believe that's my last slide. Thank you very much.
Mute. So thank you very much, Vardis, for this interesting presentation. It's great to see that such like high level, globally beneficial endeavors are using the WEkEO DIAS, and that's really space for good, Copernicus for good in the case of the European Union. So it's really interesting to see. I'm sure there are going to be some. I will personally have a few questions maybe at the end. I'm sure our audience will also have some. So time to move on to our next speakers. Our next speakers are Florence Marty and Germain Salgue. They work for a company called Magellium, which is a SME based in Toulouse, in the southwest of France. And they have been awarded a contract to develop a new product for the Copernicus land monitoring service, which is called the high resolution snow and ice product, which is a very interesting one because it is the first product in the Copernicus land monitoring service that has, let's say, very frequent updates. It uses Sentinel-2 in particular, optical satellite, to monitor changes in glaciers, snow cover, with quite a lot of very interesting applications. They're both Earth observation scientific engineers. Florence is in charge more of the documentation and of the support to the European Environment Agency, while Germain is the technical coordinator of the project. So they will explain to us what the product is about and how they have used the WEkEO cloud infrastructure to turn the product, or to operationalize, to take Vardis's words, the service, the product, into something that is robustly hosted, very regularly updated as a function of the availability of new Sentinel data, and the many use cases for this. So Germain and Florence, the floor is yours.
Thank you, Stefan. So I think now you can see our slides and hear me well. Thank you and good morning, everyone. I'm glad to introduce you with the Copernicus land snow and ice at high resolution around Europe, and how at Magellium in Toulouse we achieved to implement a system on the WEkEO platform to provide users near real-time snow and ice products. So I'll start with a brief context of the snow and ice. So historically, the information on the snow cover and ice cover on rivers and lakes are derived from in-situ data and observation made manually, and since the 70s with the Landsat mission, we observed for the first time large coverage and interesting and temporal. With those missions, we could have very interesting spatial coverage and temporal coverage that are here to complement the in-situ observation. So with the Copernicus program, as you said, Stefan, Several Sentinels constellation allow to observe the Earth, both on land, oceans, or atmosphere, for instance, and in particular, the Sentinel-1 and Sentinel-2 constellations allow to derive information about snow and ice presence over land and over rivers and lakes with a very interesting spatial and temporal coverage. So on these slides, I give you an example of two Sentinel-2 observations of the cryosphere in Europe. So on the left, we have an example of a river in Poland with an hydropower plant. So we can see the dam is covered by ice, and this can produce big issues for the production, but also transportation. And on the right, we have an example from last year with a very early snowfall in the Pyrenees. And we are now sure of the potential of the Sentinel-1 and Sentinel-2 constellation observations to provide a very interesting information for the snow and ice. So briefly, what are the Sentinel-1 and Sentinel-2 inputs we are using to derive the snow and ice products? For the Sentinel-2, those are optical images given in 13 spectral bands with various high resolution. And the revisit is of 5 days with two satellites. And it is about 1 to 3 days over Europe because we are at high latitudes. And the data is provided over tiles of about 100 widths. And for Sentinel-1, this is radar images. They are given also with high resolution. And the revisit is very interesting also, 6 days on average on the same condition of view. And it is about 1 day over Europe with observations in the morning and in the afternoon. And the data are given on tracks of 250 kilometers width. So now the potential of Sentinel-2 and Sentinel-1 observation is approved. The European Environment Agency was delegated by the European Commission to implement the massive and systematic production of snow and ice products over Europe. And now those products are disseminated since last year in the Copernicus Land Monitoring Service. And the European Environment Agency has chosen a consortium with various scientific partners all around Europe. And this consortium is led by Magellium, so this our company in Toulouse. And now we are producing in near real time those products that are very interesting for various actors. In the energy, I think about the hydropower production, for instance, but also the transportation on the issues we can encounter due to snow events in the airports in Madrid, for instance, remember last January, but also for environment issues and how to better manage the water resources. So of course, to meet the user requirements, it triggers some technical requirements. In particular, users want large coverage and high resolution products for their various needs. And they also require historical data. For the Sentinel-1 and Sentinel-2 satellites, the data are available at least from 2016. So it represents a large amount of data to process. And to give you an idea, every day there's about 800 products to process from Sentinel-1 and Sentinel-2 over the EEA 39. This is the area on which high-resolution snow and ice from the CLMS are disseminated. So this high volume of data requires a massive and also a reliable computation resources and storage capacity. But in addition to this high resolution and large coverage, the main point, the main idea here is to provide the users with those products in near real time. Ideally, within 6 hours after the sensing from Sentinel-1 and Sentinel-2. So this near real-time availability is very crucial for time-critical applications. And for this, it requires efficient computation and the quick availability of the input data by the Copernicus hub. So here is why we have chosen WEkEO, the WEkEO Dias, to implement our system, snow and ice system, for the generation of the snow and ice products. Because WEkEO allows an automatic input data provisioning directly from the Copernicus hub. It also allows a dynamic allocation of the processing resources, and the high-resolution snow and ice products are also available on the WEkEO interface for visualization and download. So here, I'd like to emphasize that finally, at Magellium, we successfully achieved to implement a system that produce and disseminate the snow and ice products thanks to the WEkEO portal, thanks to the WEkEO Dias. And this is the first operational production use case in near real time in such a context for a Copernicus service. So now I let the floor to Germain. He will give you a brief description of the products. Thank you.
Okay, thank you, Florence. In the production, we have different type of products that are generated. Here is a summary of the snow products that are produced in near real time, or almost near real time, because there is also aggregated products that are produced in daily time and that are more aiming to a long-term monitoring of the cryosphere. So the first product is the fractional snow cover, which is produced in near real time for each Sentinel-2 product as input. As mentioned, and as for most of the cases, the spatial extent is on the entire EA39, and the data is projected in UTM. So this product is providing a fraction of snow for each 20 meters by 20 meters pixel. It is provided at top of canopy, but also on ground using the information of forest density. And here is at the look of the product. Then we have a product that is directly based on this first one, which is the yearly aggregation of the information, and for which we retain only the persistent snow area. So it gives the snow cover that never melt, or also part of the glacier. And it is a picture in Iceland, for example. We also have products derived from Sentinel-1 data, and in this case, the WDS is a combination of the fractional snow cover and the S1 information to provide an accurate wet snow mask information combined with the S2 observation. We also have the SWS, which is a SAR-only product that is providing the wet snow information, but it is generated only on high mountain areas, so the main mountain areas in Europe. And finally, we have a product that is gap-filled fractional snow cover. It is using both wet snow and fractional snow cover information over the past 7 days in order to provide the best mask possible, trying to fill the cloud when there is snow information, either from Sentinel-1 or from Sentinel-2. The second part of our product is the ice monitoring. So we have the river and lake ice extent, which is computed from either Sentinel-1 or Sentinel-2. And we also have the same product, but this time from the combined information of Sentinel-1 and Sentinel-2. It is computed over the WEkEO, which is the hydrological network over Europe, and provide the state, either ice or snow-covered ice, and snow-free water area. And the last products are also a combination of information, and it provides statistics over each river section that was splitted in 10-kilometer section. And we can retrieve the ice and ice-free information percentage over the period, and in our cases, it's for 1 month over this section. So it's a great tool to compute statistics and have an idea of the cryosphere in time over time, and also within the year and within a specific spatial extent. And so all these products, to generate all these products, we have set up an entire system based on the JAS cloud infrastructure in order to generate and provide in a reliable way all these products. Just to give a quick overview of what was done, we have mentioned that the DIAS is providing the access to the Copernicus hub data, so in particular the Sentinel-1 and Sentinel-2 data. So we have this direct link through the DIAS catalog to access in near real time this information. And then we have developed a central service, the high resolution snow and ice system, which is an orchestrator that is using this DIAS catalog and also external auxiliary data like the digital elevation model, like the WEkEO network, to generate all these products. We can monitor with an external interface this system. It will be presented in a few slides. And we provide a complete access to all our products. We have WMS, we have HTTP request, we have the link on the CLMS portal to the description of the product and the link for the data access, and also the availability through the WEkEO web portal. So what does it mean to set up such a system on a cloud infrastructure? So as I mentioned, the central point is the orchestrator. And for this orchestrator, we have relied on OpenStack and all the module and some of the module available. This is the main component, because without OpenStack, we would have we wouldn't have been able to allocate the numerous virtual machine and all the resources that we need for the processing. In the heart of the system, we also have a PostgreSQL database to centralize all the information for all the tasks that are required. Also, we use the capability to allocate different virtual machine flavor. So in particular, from 2 virtual cores, 4 virtual cores, 8 virtual cores, and so on. There is a lot of possible configuration that was used to optimize the resources needed depending on each type of job and the amount of data to be processed. And for the storage, we are using the standard capabilities, which is the S3 object storage. Basically, it is a network storage that can be shared and accessed on internet, for example. And just to give you an idea of the size of the system, it represents up to 920 virtual CPUs dynamically allocated. about 100 terabytes only for the produced data, so for the output product, about 10 terabytes for running the system, so the database, the auxiliary data, and all the information that need to be persisted. And for the system itself, so for the orchestrator, we have 10 virtual machines running 24 hours a day to maintain all the service up all the time. So now I will show you what is the service and where are the products. We are mainly on the CLMS portal, where you can access the high resolution snow and ice monitoring. You have the snow product, the ice product, and the direct link to the data access. You can read more about our product on their description. There is different link leading to each of the products. For example, if we follow the snow product, we retrieve all the product that we have defined, and in particular the snow cover in this example, derived from the Sentinel 2 product. There is the description of all the algorithm and the link to the metadata, to the validation report, product user manual, and also the ATBD. So now we are also showing how we access the data. There is a link of the CLMS portal that is redirecting to the WEkEO web interface. So I am starting by removing the default layer that are provided. You can see that there is a cartographic background. You can access the CLMS land category, and in particular the cryosphere. And here you will see all the products that are already integrated. There is more product coming in the next few weeks. You can select each product and each layer within this product. So, for example, the fractional snow cover on ground, it is added to the map, and then you can go on and select, for example, the river and lake accent, add it also to the map. And then to see the data, you have to zoom in and select your area of interest. So this example was recording early in this week. So all the products that will be displayed at this location are the most up-to-date information that we have on this area. So it takes a small time to load the information. So first, the low resolution layers, and then you will see that it is refining. And then what it is refined, you can zoom and see pixels up to their resolution of 20 meters. So you can see that the detail is quite accurate, and it is a very powerful tool to see all this information. You can, for example, remove some layers by playing on their transparency to see the perfect match with the underlying layers. And then, of course, you will be able to download all this data by clicking the download button. And for this, you will have to be registered on the WEkEO portal and follow all the tutorials that are available to access the different datasets. So, as I mentioned, we have a dashboard to monitor the system, and in particular, a first view that allows to see the health of all the services that are needed for running the system. Once the operator has seen the global health, he can access the detail about the different job, and starting by the summary of the job process during the past 24 hours. You can see the number of products that were created, the number of products that are completed, and also the number of products that lead to an actual product, mainly because of the cloud coverage. We have the difference in terms of publication between the availability on the Sentinel 2 data on the ESA hub, and then on the WEkEO interfaces, and finally with our product generation. So we can see that we are able to produce in about 1 hour and a half after the publication by ESA of the product. We can also see the arrival of the Copernicus product. there is their sensing time, because for the user interest, it is not the publication on ISA that is interesting, but the delay between the acquisition and the actual availability of the product. And we can see the same pictures for the Sentinel-1 data, their sensing time, their ISA publication time, and finally their availability on the DIAS before we start the processing. And to see the processing in detail, we have the complete list of each job that are triggered, and we can follow their execution. We can follow their state and see what is happening in near real time, in real time in this case. And for example, we can filter on the completed product that actually generated a product. There is the complete list with all their status, and when we go below in this dashboard, we can have more detailed information. For example, the exact change of each task from the job creation to the completion. And that concludes our presentation on the system. So it was a bit quick in terms of dashboard, but there is a lot of information, and it is a very complex system. So we would like to thank you. If you have any question about the high-resolution snow and ice product, you can reach the CLMS help desk, or directly contact our technical teams at cosims@magellium.fr. Thank you.
Thank you, Germain. Thank you, Florence. Quite impressive to see the amount of processing power and storage, cloud storage, that you've been using for this groundbreaking product, because indeed, as said, it's the first time that there is a near real-time product being made available by the Copernicus Land Monitoring Service, because the dynamics, obviously, of snow and ice are high, and therefore such applications are required. Running a bit late, but I will now pass the floor to our two next speakers. We're going to change completely type of applications, and we're going to talk about monitoring and forecasting air quality at very local level. And for this, we have two distinguished speakers. One of them is Bas Meeling. He is an air quality scientist at KNMI, the Dutch Royal Meteorological Institute. He has a PhD, and he has a strong specialization in monitoring, in particular, nitrogen-based pollutants. And he has developed within a European-funded research project, or co-funded research project, a system, a methodology called Retina, which is basically the engine behind the Lobelia Air application that will be showcased today. And our second speaker will be Aitor Naranjo, who is the business development director of Lobelia. Lobelia is a small SME located in Barcelona, Spain, and they're very active in climate services, in air quality monitoring, and we're going to talk about it today, and also in marine applications and marine and visualization. They do also great visualization systems for Copernicus Sentinel data. So, Bas and Aitor, the virtual floor is yours.
Okay, hi everybody. Let's switch topic. Like Stefan said, thank you for this introduction. Please, Joanna, can you help me out with the presentation? I can do it myself. So here we are.
Oh, lovely. Love working. Yes, go ahead.
We are running behind schedule, so I will walk you fastly through our application. It's about urban air quality monitoring. I think it's a very important topic, because more than half of the world population is living in cities, and it is in cities where people are exposed to exceeded levels of air pollution. And air pollution, as you know, is an invisible killer. You cannot always see it, but it's there. And it's the problem is that it's very hard to monitor. It's expensive to monitor. So what we want to do is make better use of the available measurements of air pollution to get better insight on what's happening of air pollution on a street level. So we're focusing on the main players of urban air pollution, which is nitrogen dioxide, NO2, and particulate matter, PM, which have different characteristics but are varying from street to street in urban areas. So they have to be watched over carefully. So we also want to do, what we obtain to do is make forecasts, 24-hour forecasts, so people can anticipate of upcoming pollution spells. And we developed two systems for the city of Madrid and Amsterdam, which both are running happily on the WEkEO DIAS for more than 2 years now. And happily means that we have good support from the WEkEO team and perfect uptime. So I give you some background information about the algorithm before I give over the presentation to Aito, who tell us more about the application and dissemination towards the public. Traditionally, like I said, air pollution is monitored by the official reference network operated by local authorities. But as I said, they are very expensive, they are huge, difficult to and expensive to maintain, so they tend to be very sparse. So at the same time, you see that there are new developments in monitoring techniques, and from space there is this Tropomi instrument, which our institute is responsible for, which has been launched over 3 years ago now, and it is really the capacity of doing air quality measurements within the urban area. So this is very practical and nice additional material. Complementary on the surface level, you see that there's more and more upcoming new technology regarding low-cost sensors. So depending on the budget, the cities are experimenting themselves with mid-cost solutions, or even citizens starts to measure themselves to get, to fill in the knowledge gap of air quality. So here, just to give you a flavor, an example of what we can see with the Tropomi instrument on Sentinel 5P. For a particular day over Madrid, you can see clearly the strong concentrations of NO2 over the city center, and even the plume of pollution floating, swirling to the southwest, eventually to the southeast. So this is from space. On the ground side, you can. I want to show you this. This is the Sensor Community Initiative, previously known as Luftdaten, where people can buy on their own account very cheap parts on Chinese web shops and build their own air quality measurement device. And people are doing this by the thousands. Actually, this is an example for Milan, but at thousands of locations around Europe and over the world, people are measuring their own concentration of PM and publishing it in a central database. But the frustration, my personal frustration as a scientist, is that these kind of initiatives usually end up as dots on a map, and that's not very convincing to show what's really going on, and it's not very practical feedback to the audience or to the stakeholders. So what we are trying to do is combining all these heterogeneous data sources we have in high spatial resolution maps with an hourly time resolution. So what we're dealing here is a spatial interpolation problem, because we don't want to rely too much on air quality modeling. We only need the air quality models to fill in the knowledge gap between the measurements. So if on the red side here, this is like the traditional starting point we had, let's say a few decades ago. There were very few measurements, so you need a very good model to predict the rest of the urban environment. And in the ideal case, you would be on the green edge of the spectrum. There would be so many measurements that the spatial interpolation would be so easy, and a sloppy model would be sufficient to do so. But in reality, we are somewhere, I would say, in the orange or yellowish part, depending on the city. which means that we still have to do quite some important modeling effort before we can start a data simulation. Okay, this is why we came up with the Regina algorithm. It has some design features I want to share with you. Like I said, it's observation driven. I really use observations as a starting point. And we want to be able to assimilate observations of different accuracy. So both the reference measurements, which are very accurate, as low-cost measurements, which has significantly higher in accuracy. Also, we're looking for a solution which is portable, so it can be easily implemented in other cities as well. So we don't want to be attached to one city only. So it means that we have to find a solution which is based on open data, which is readily available for different cities across the world. And finally, we want to have a system which can work with reasonable computer power. So we do not want to depend on high performance computing just to do a spatial interpolation. One of the main problems we encounter if we want to set up urban air quality models with such a high resolution is the local emissions, because local emissions are not well known. Fortunately, we can approximate the location of these emissions, especially in areas where pollution from traffic and from residential emissions is dominating, such as in urban areas. So what we do here is take data from open data sets like OpenStreetMaps to get the information about the road network, the road type, and also get information from data sets like the Global Health Settlement Project, which gives us information about the population density, because we know where the population is more densely present, there are more emissions by humans. So this we can do easily for whatever city we are focusing on. So once we have our emissions, our local emissions, we also need data from the weather, the meteorology, which we take from the ECMWF. We also heavily depend on a good approximation of the background concentration of the air pollutants. And this is where the CAMS regional ensemble really comes into play. From the CAMS ensemble, we take the background concentrations for NO2, for PM, and also ozone, for instance, which is important to do the chemistry within the modeling. So this we feed in our dispersion modeling, and we calibrate the model in such a way that it nicely fits the observations of the ground network. This is the calibration phase. So we use recent historic measurements to do this calibration, and once calibrated, we can do a forecast of what the concentrations are now, or what they are in the recent future, or in the next future. And these fields are combined with the local observation network to do the data assimilation with. And for this, we use an optimal interpolation scheme, which means that we take into account the errors of both the model and the observations. So that means that we are able to assimilate in situ observations with different accuracy. So that means that we can use both the reference measurements as low-cost measurements at the same time. Okay, this is to give you a flavor of how well it works. You see here on the left-hand side a monthly average of the Madrid concentrations, October 2019. But actually we are predicting or providing hourly maps. So in the scatter plot you see the hourly predictions by our system compared against the observations from two stations. And the middle one is a street station, and on the right-hand side you see a typically urban background station. And we do this validation with a leave one out cross analysis, which means that we use the measurements of all the other stations in the network except for the reference one to validate the time series we produce with. So basically what you see in this data simulation exercise is that the accuracy, of course, depends on both the accuracy of the air quality model, but also on the amount of assimilated observations. So the more observations we will put in, the better will be the results. But also the quality of the observations, the more accurate the observations, the better will be the results, of course, as well. But also the distance to the observation location. So if we are further away from an observation location, we depend more on the forecast of the model, and we depend less on the measurement itself. So this is what the optimal interpolation scheme does, this balancing between these two areas. So we did this implementation for Amsterdam and Madrid on the WEkEO platform. In parallel, we also do this for Barcelona on other cloud infrastructures. Typically, we find errors of about 30% and quite high correlations about 0.85 on an hourly level for most validation sites. And our future work will concentrate on more actively use the satellite data from the Tropomi instrument and ingest more low-cost data from local urban campaigns. So this is where my talk stops, and Aito will take over from here and tell us everything about the monitoring and forecast service. So please, Aito, go ahead.
Thank you, Bas, and thank you, WEkEO, for organizing this webinar and for inviting us to present our operational service on urban air quality monitoring and forecast. So Bas has presented the engine. I wanted to focus on different aspects. One is the operational aspects. So for the service to work continuously on 24/7 basis, it's very important to implement alerts on both the input data and the output data, as well as the data that we are receiving from APIs. The idea is to fix the issues before they affect the users. Then a resilient backend is fundamental. So as Bas explained, the raw data is processed on the WEkEO environment. This is sent to the Aircast, the air quality and forecast platform, where this raw data is post-processed by Lobelia and converted into analysis-ready data that is integrated in the Lobelia Air service in order to distribute the maps, the data through API connections or through a web app. So for the final users to see the results. And it's important to mention that we had a very high uptime, almost, it's not 99.9. Actually, I just checked with my colleagues, and it's 99.5 in the last 15 months. The customization is important. We do it at the API level, so the users can access the area of interest or point of interest through the API, as well as the routing system. We do custom UX, so that applies for multiple audiences, different languages. We adapt the branding to our different customers, as well as we have specific features, add-ons, services to the existing monitoring and forecasting, as well as a responsive design, so the service works particularly well on mobile and other devices. So this is an example of one of the services that is contracted by the Barcelona Greater Metropolitan Area, so the Department of Mobility and Air Quality. This is on the left-hand side, you see a map of Barcelona that the different colors show the concentrations of NO2. At street level, you see that there's more concentrations on the ring around the city, and in white here where my arrow is, that's the the time series that we're showing, so from the past 3 days. And then this bar here would be the current moment, and then the forecast to 24 hours that we have developed at Lobelia using a neural network. And here on the time series, we see the thresholds for the annual limits from the WHO guidelines, and then the hourly limits here. It's important to mention that yesterday the WHO changed the 2005 guidelines, and then the limits on pollutants are more restrictive now. So we're gonna have to change this in our visualization. So we are very much looking forward to this. Then on the right hand side, you see a zoom in on this area. So that shows you the very high resolution of our service. Then another example is on the different area points of interest that we can show, in this case for vulnerable groups. So on the right hand side, you see the map of the municipality of Madrid, which is another of our customers, and they're using our service operationally, the Department of Air Quality. Madrid is one of the cities with the highest burden of mortality due to NO2 levels, and here the point of interest in this map on the right, in the green dots are schools. So you click on each school, you will have the concentrations of NO2 on micrograms per cubic meter, and then you can define a buffer zone around this area. So you can see on the left-hand side, that would be a similar feature, but for playgrounds. So then you have this buffer zone, 15-minute walk, where you can choose the playgrounds with a better air quality. So you can go there with your family if you wish to. Then another feature example is the routing application. So we have developed a routing algorithm that takes the input from the monitoring service to get the concentrations of pollutants en route, and then it compares it to the fastest route, which will be using an algorithm like the Google Maps routes. So the fastest against the healthiest, and this is used by the greater metropolitan area in Barcelona, and that is covering 36 municipalities with over 3 million inhabitants. So this has this service that is, as I already mentioned, operational, and that we have paying customers, have generated an important social impact. When we launched the service a couple of years ago, well, actually right before COVID started, we generated a free data set of hourly concentrations of NO2 at street level for the whole 2018. And a grassroots organization from Barcelona that is advocating for better air quality used this data set to produce a ranking of the 750 schools, public schools in Barcelona, to rank them according to the pollution levels during lective hours from 9 to 5. And that had a very high impact. So not only at media level or at parents, students, associations level or schools, but also at the departments of education, air quality in the city council, and some actions were taken, like eliminating lanes in very busy streets, so not allowing parking in front of schools, and so on. And this organization, this grassroots organization, now is promoting for over a year a protest every last Friday of the month. The schools are cutting the traffic at the end of the classes at 4 or 5 o'clock for 30 minutes, and this has triggered that this movement is now in 116 schools from 16 Spanish cities today, and is growing. So very efficient way to sensitize citizens, to provide data, observation-based data at very high resolution. So that higher citizen interest had led to increased media coverage. And the image that you see at the bottom, that's actually another of our clients, which is the weather section at the Barcelona Public TV. They're using our map, which is embedded in their website, but also during the exceedances of air pollutants, during the days of exceedances, I want to say, they are presenting the maps when the weatherman is talking at the evening or morning news. And there's actually a QR that they included, so people watching the news, they can go to their service and see the quality of the air in their area of interest. So that has proven to increase the traffic of the service. So we have seen that on our Google Analytics. So just to summarize, our system is fully operational with regular validations. It is available in 3 cities with paying customers. We have different add-on services, such as the healthy routes. We can implement the system in a new city in a very easy and simple way, and we're capable of ingesting data from heterogeneous sources, like low mid-cost sensors as well as satellite data. And we have customized UX for different campaigns, for behavior change and active mobility. And that would be the end of my presentation. If you have any question for me or for Bas, we will be happy to respond. And if you want us to send us an email, you can do it at aitor@lobelia.earth. Thank you very much.
Thank you, Aitor. Thank you, Bas. I find it quite extraordinary to see that open satellite data from Copernicus, with citizen science and crowdsourced information, with in the middle a powerful engine, powerful backbone such as WEkEO, can produce things that have a direct benefit to individual citizens, which is at the end of the day really nice to see, and also a social impact. Really very, very interesting. So we saw a rather, let's say, a marine application, we saw a land application, we saw an air quality application that nicely also illustrates, and I'm answering a question through that, the fact that the Sentinel satellites of Copernicus cover both land, cryosphere, sea, ice, air pollutants, ultraviolet, etc., etc. There's really a very wide range of data that is available within the WEkEO DAS. I haven't seen many questions. There was one that has not been answered directly in the chat. It's about what is the internet speed that you need to be able to use the service. What I can say is that because everything is processed in the cloud, because what you download at the end of the day is only a small, rather light file, it can. I personally have used the WEkEO, at least data discovery, where you can actually look at the let's say Sentinel-2 data, optical data, for instance, and then download the JPEG. I've used it from my computer with a 4G chip in the computer. It might take a little bit longer to display the image or to refresh it, but you don't need to have a super high broadband link internet access to process the data. That's the answer to that question. I haven't seen any more questions. So if there are no questions, I would like to very much thank the presenter, because I think we showed a broad spectrum of use cases, from, let's say, science to land monitoring applications. And if you think of the snow and ice product for ski resorts, for companies that own hydropower and need to know how much water they can expect to be in their reservoirs, irrigation, road transport, rail transport. The beauty of Copernicus, which you can access through WEkEO, is basically the imagination of application developers and service providers is the limit to what you can actually do. So that's quite interesting. So I see no other questions. So I want to thank our auditors once again. This webinar, as well as all the previous 11 ones, will all be available on our YouTube channel. We're working and will shortly announce a new program of seminars. This was the first one of the last one of the first cycle of WEkEO webinars. Follow us on Twitter or visit our website at wekeo.eu to stay tuned with the upcoming program of WEkEO webinars. Thank you all again for your participation, and have a great rest of the day. And thank you indeed very much to our 5 presenters, who really showed a wide palette and some really cool and interesting applications in very varied application areas. Thanks again.